Welcome back to Larry's Classroom. Today we're going to talk about voltmeters. We've discovered that the meter movement, it responds to current. We'll put this down as a 1 milliamp. 1 milliamp for IM, which is the full scale of the meter. And we'll also put Rm, the resistance of the meter is equal to 50 ohms. Now, there you go, there's a picture of the meter. This meter movement responds to current, but we can use this as a voltmeter by adding a resistor in series with it, which we call a multiplier resistor. We'll call this, just call it R1. We'll put some polarities on here, negative and positive. The resistance of the meter is usually low compared to the circuit that you're working in. So if we were to use it directly across for a voltage reading, like right across a battery or something, we'd have too much current and it would just peg up. But when you add the resistor in series with it, now it becomes a much higher resistance or much higher impedance, so we can put it across different components to read the voltage, like directly across the battery, for example, rather than having to break the circuit to put it in series. So we'll put a battery up here. And this is a 20 volt battery. $20, negative, positive, which is going to lead to a current going, electron flow current, not conventional current flow, through the meter and back to the battery. We get a complete circuit that way. And 1 milliamp is a fairly low amount of current. 1 milliamp is equal to 0.001 amps. So it's 1/1000th of an amp. But we want this meter to be able to go to full scale with 20 volts. So how would we do that? We need to have enough resistance in this circuit to limit the current to 1 milliamp. So we need a total resistance of, well, we got our resistance is equal to voltage divided by current. We know the voltage, 20 volts. We know the current, which is the current of the meter. So let's calculate that out, see what we come up with here. So if we take, we want R to be equal to the voltage of the meter, the voltage of the supply, or the voltage of the range that we're trying to design this voltmeter circuit for, 20 volts, divided by 0.001 amp. Well, dividing by 1,000 is yeah, that's going to be 20. Oh, we need 20,000 volts total. That's what, okay. Or 20,000 ohms. Yes, we're going to need 20,000 ohms to total resistance to make this into a 20 volt range meter with this 1 milliamp meter movement. But we have 50 ohms for the resistance of the meter. Let's put that symbol omega on there. So we need to have a total resistance RT. Well, we have RT. This is RT. We need to have R1. What's R1 going to be equal to? Well, our total resistance is going to be, RT is going to be equal to R1 plus RM, resistance of the meter. So we have this value. We need to find this value. Well, RT, 20,000 ohms. Then we'll subtract from that RM of 50 ohms. And that becomes 19,950 ohms. So R1 here will be 19,950 ohms, our multiplier resistor as we call it, which turns this current meter into a voltmeter. Now we can put this across any voltage. If we put 10 volts in there, basically the current would be half and our meter will read halfway. So with 20 volts supplied, we're going to get full scale deflection here. We're going to read 20 volts. Over here on this, let's put these down here. 20 volts, 0 volts, and in the middle we're going to have about 10 volts. So when we apply a 20 volt source to that, or 20 volt supply, 20 volt, we could be reading the voltage drop across resistor, we could be reading the voltage of a battery. We will get 1 milliamp of current will go full scale. If we put it across a 10 volt, the same circuit, nothing changes other than the voltage. Now we will get a half scale reading. We'll get a half a milliamp, and our meter will go up to halfway, and we will calibrate the scale to match what we designed this meter to do. And let's see if we take this 1 milliamp movement and we want it to be a 1 volt meter. Well, okay, how much total resistance would we need? RT would be equal to the voltage range that we're looking for. We're looking for 1 volt, and we're going to divide that by 0.001 amp, or 1 milliamp. When we do this division, we end up with 1,000 ohms. So this creates what we call a 1,000 ohm per volt voltmeter. And as you recall, when we set it up for 20,000 ohms, or for 20 volts, we end up with 20,000 ohms. And this is going to be the total between the multiplier resistor plus the resistance of the meter. So the formula for solving for that, which we kind of just introduced, but we'll go over again. We want to know our multiplier resistance. Our multiplier, we'll call it. We will take the full scale voltage that we desire for our meter, divided by the full scale current per meter. Current of our meter movement. And as you can see, this is R equals V over I. Voltage V, current. It's just an application of Ohm's law to give us a resistance. But that's our total. This is the total resistance. This is what we'll call it RT. So we got to subtract from that the resistance of the meter, which usually be given to us, or maybe we could measure it, but we subtract from that RM. So if we're looking for the value of our multiplier resistor, we need to find the total needed resistance, which is the voltage that we want to apply. That was 20 volts for full scale. We'll go back to full scale here. The voltage that we desire for full scale, divide it by the full scale current meter is, in other words, how much current it takes for the meter to get to full scale, that gives us our total resistance, which is going to be the sum of the multiplier resistance and the meter resistance. So let's just call this little big RM, and that guy's little rm. So that M stands for multiplier now, rather than saying R1. Capital RM would be multiplier. Little rm is the resistance of the meter. But the sum of those has got to equal this RT. So we calculate RT. We subtract from that RT the resistance of the meter. So now let's apply that formula once. We have, I'm going to change the values right up here. We have a meter movement which has an IM, full scale, of 50 microamps. Which would be 50 times 10 to the minus 6 amps, or 0.000050, 4 zeros and the 50 on it, but 50 microamps. We have a RM given to us for this meter, which is 2,000 ohms. And we still want to do a 20 volt full scale like we did before. And remember, with the 1 milliamp movement, 20 volt scale, RT was equal to 20,000 ohms. We'll put that up there, remember, and the sum of that RM and the meter movement came 20,000. And that was, as you remember, was 1,000 ohms per volt. Now this guy, 50 microamp meter, is going to take far less current to get to full scale. So we're going to need a bigger value of RM to limit that current to 50 microamps. So we're going to apply this R multiplier, and we're going to put in R mult. We're going to apply that formula. It's going to be the full scale voltage that we're looking for. We're looking for 20 volts. The full scale meter movement, which is 50 microamps. And from that, we're going to subtract the resistance of the meter, which was given to us as 2,000 ohms. Well, if we work that out, this becomes 400,000 ohms. Let's put the ohm symbol on it. Minus 2,000 ohms, which leaves us with 398,000 ohms. Or we also call that 398K ohms. Now, what do you notice? The total resistance of the voltmeter that we created when we use the 50 microamp meter movement rather than the 1 milliamp movement, we end up with a higher resistance, so it's going to put less load on the circuit. You recall we talked about loaded voltage dividers and stuff, how it could swing the voltage. Well, the same thing applies when you put a meter across the circuit. You are loading whatever your circuit is, and the less we load it, the more accurate your reading will be on this meter. And let's do one more thing here with this 50 microamp movement. If we wanted a 1 volt, so we're going to RT 1 volt divided by 50 microamps. That ends up being 20,000 ohms. Ohms per volt. So the 50 microamp meter creates what we call a 20,000 ohms per volt meter, which means that the voltage range that we wanted, which in this case is 20, well, 20 times 20,000 is 400,000. the meter movement, which requires less current to swing it to full scale, needs a higher resistance, so it ends up putting a lesser load on the circuit. The 1 milliamp movement gives 1,000 ohms per volt, or only 20,000 ohms for 20 volt range, where this meter, the more sensitive meter, ends up being a 20,000 ohm per volt meter, and it, for the same 20 volt range, we need a total resistance of 400,000 ohms. So 20 times as much resistance, 1/20th as much current, a lot less load on the circuit that you're dealing with. And consequently, you get readings that are closer to the actual readings when the circuit doesn't have the meter across it. We put voltmeters, we put across components to read the voltage drop or the voltage supply, if it's a supply. There's no difference when you're reading with a voltmeter between reading the voltage drop across the resistor or reading the voltage of a supply or a voltage source. Well, we're gonna design a meter with multiple ranges now, using this same principles that we've been talking about. So we're going to start with a meter. We're going to put a meter movement here. And this meter movement is again IM of 50 microamps. So this is the same meter movement that we just used in our example, our first example. And it's going to have an RM of 2,000 ohms. Same characteristics that we just dealt with here. We'll draw the needle in there. And we're going to put the negative side of the meter here and the positive side of the meter here. So current electrons flowing from negative to positive will swing the meter over to the right to full scale. And we're going to put a range switch. We're going to have 1, 2, 3, 4. We're going to have four ranges on this meter. And we're going to have a selector switch that allows us to select different ranges. And we're going to have a 5 volt range. We're going to have a 50 volt range. We're going to have a 250 volt range. 250 volt. And we're going to have a 1,000 volt range. Now basically this switch is going to select different values of multiplier resistance. So we're going to draw our multiplier resistors up here. Being we got 4 ranges, we're going to need 4 of them. We call this R1, R2, R3, R4, and they will correspond to the different meter ranges. So we're going to connect some wires up there to the junctions between these resistors. So now we have 4 resistors, and okay, we're going to run this out to our positive lead of our meter. And this guy over here is going to go out to our negative. A lot of times on a meter you'll see little sockets in the front of it for connecting the test leads, and it'll be labeled negative and positive. You're always going to see some kind of labeling. So these will go to our little sockets where our test leads plug in. So let's look at what we got here. If we're in the 5 volt range, our current goes through the meter, through R1, and back to whatever let's just put a unknown source value here, a battery of unknown voltage, and we'll just pretend like we're reading the voltage across that. Let's use that. That's all right. So we have a negative and positive. It could be a battery, it could be a resistor that we're reading across. But for now, we're just going to say it's a battery. So if we're in the 5-volt range, current will flow, electron current will flow from the battery, electron flow through the meter, through R1, back to the battery. If we go up to the 50-volt range, now electron current will flow through the meter movement, through R1, through R2, back to the battery. If we go to the 250-volt range, electron flow goes through the meter movement, through R1, through R2, through R3, back to the switch, and back to the battery. If we go to the 1000-volt range, current will flow through the meter movement, through R1, through R2, through R3, through R4, back to the range switch, and back to the battery. Well, let's label this. Let's put a kind of a dotted square around this thing. And that's called the range switch. And if you've ever messed with a meter, you've probably seen there's a switch on there for selecting different voltage ranges, and that's what this guy is here. So now we're going to do a little bit of calculations. First, let's see what the I'm going to erase this battery and get it out of our way because we don't really need it there. We're going to need some room to do some calculations. If this was a 1-volt meter, we would need a total RT would have to be equal to 1 volt divided by 50 microamps. And if you do the division, this with your calculator along here, this comes up 20,000 volts. 20,000 ohms, I mean. So this is what we call a 20,000 ohm per volt meter. 20,000 ohm per volt, we'd call that. So let's do our calculation. What do we need R1 to be for a 5-volt range? We call this range. So we need, let's put our RM formula here. RM equals voltage range divided by IM, which is the current rating of the meter, minus the resistance of the meter. We're going to use this formula to solve each of these. We're going to figure out what RT we need. For each of these ranges. So RT for 5 volts is going to be the 5 volts divided by the well, you can do it two ways. Let's do it. We could do the 5 volts divided by the current, and we would end up with 100,000 ohms, or we could do the 5 times the 20 too. Either way, it's going to be 100,000 ohms. We're going to write 100K minus 2,000 ohms, which is equal to 2K. So we would need a total of 98K ohms. So R1 is going to be 98,000 ohms, 98K ohms. So we put that, it's the only one in the circuit. We have 100,000 ohms total. It's a 20,000 ohm per volt meter. The The 100,000 divided by 20,000 is 5, so that gives a 5 volt range. Now, we're going to have a different RT for each voltage. We're going to do the 50 volt range. Well, if we either do 50 divided by 50 microamps, or we do 50 times 20,000 volts, we end up with 1 megohm. We're doing RM here. RM was 100K minus 2,000, which gives a 9. RT is 1 megohm here, 1 million ohms. And RM is going to be 1 megohm minus 20,000 ohms. No, 2,000 ohms, excuse me, minus the meter movement, which is 2,000 ohms, which works out to be in okay, no, it's not going to be minus 2,000 ohms, excuse me. RT needs to be 1 megohm. But we have to subtract out of there. Now we're going to be taking out R1 and RM. Well, R1 and RM was 98 plus 2K, which is 100K, or that's 0.1 megohm. So we end up with 1 megohm minus 0.1 megohm, which leaves us with 900 K ohms. So we're going to need for R2 900 K ohms. The 900 plus the 100 gives us 1,000 K ohms, or 1 megohm. So that gives our 50 volt range. Now what do we need for RT for the 250 volt range? RT 250 times 250 volts times the 20,000 ohm per volt, or we could do the 250 minus the current. We get that. No, yeah. The 20,000 ohms per volt. Yeah, this meter, this only applies to when you're doing it a little bit differently. So we need 20,000 ohms per volt. We figured out that for this meter. 250 volts, so we need to have, that's 5 megohms, right? Yeah, it's 5 times as much. We need 5 megohms total. But we already have 100K plus 900. We already have 1 megohm, so our RM for this range total has to be 4 megohms. So we got R3 equal to 4 megohms. And you can see that the 100 plus 900 is 1 megohm plus 4 more. In the 250 volt range, we have a total of 5 megohms. For the 1,000 volt range, well, what do we need? We need 1,000 times 20, so we need 20,000 ohms, or 20 megohms, don't we? Total. We need 20 megohms total resistance. Well, we've already got 100,000 plus 900,000, 1 megohm plus 4 megohm. So we've already got 5 megohms. So we need to go 20 megohms minus the already 5 megohms that are in there. That leaves us with 15 megohms, 15 million ohms. So we're going to need a 15 meg ohm resistor here to give us the 1000 volt range. I'm going to write these ranges up here. You see them a little bit better. 5 volts, 50 volts, 250 volts, and 1000 volts. So if you've ever used an analog type meter like a Simpson or something, this is basically what's in there. There's a meter movement, and 50 microamp is kind of a standard. There are probably better ones than that too, but a standard fairly high impedance meter, which is probably a little bit obsolete now because everything's digital, but nonetheless, this allows you to get reasonable readings on electronic circuits. So we calculated 5 volt range. We have a total of 100,000 volts. 20,000 times 5 is 100,000. The 50 volt range, we have a total of 1 million ohms, or 1,000,000. Well, 50 times 20,000 gives us that 1 meg ohm of resistance that we needed. The 250 volt range, we got the 3 resistors. The total of them ends up being 5 meg ohm, but these total add to 5 meg ohm. 20,000 volts per 20,000 ohm per volt times the 250 volt gives you the 5 meg ohm, which is the total of these 3 plus resistance of the meter. For the 1000 volt range, again 20,000 ohms per volt times 1000, that gave us a 20 meg ohm total resistance needed, and the resistance of the meter plus the resistance of R1, R2, R3, and R4 with these values add up to 20 meg ohms. So we create a 4-range voltmeter, which these would be sufficient ranges for most stuff. You know, you'll see different things on different meters, but this will work out for most applications. Now we're going to talk about how much the meter impedance or resistance affects the reading of the meter. We got a little formula for that. Well, we're not going to move to that just yet. We're going to draw some circuits and make some examples. Then we'll talk about it. We won't talk about the loading effect of a voltmeter on a circuit. We're going to use a voltage divider example like we have done so many times. 50k ohms here, 50k ohms here, R1, R2 equals 50k ohms. And we're applying 50 volts. And now the meter we're using now is a 1 milliamp meter, which you remember that we had the meter movement with IM equal to 1 milliamp, and we're not going to worry, we'll put RM up here, but we're really only interested in our total here. That was 50 ohms, right? The 1 milliamp meter, 1 volt divided by 1 milliamp, equals 1 volt, 1,000 ohms per volt. So if we want to do 50 volts, we need to have 50,000 ohms. So we put our meter across here. That meter, I'm just going to draw a box and I'm going to write 50k in there. So now initially, before this was hooked up, We got a very simple voltage divider with both of the resistance the same. So we're going to end up our VR2, we call it V2, is going to be 25 volts, right? Half the voltage is going to appear across there. Now when we connect that up, we've got a new voltage divider. We have now REQ of 25 k ohms. Now let's not put that there. Let's just put it right here. REQ of 25 k ohms. And that is the resistance of the 50 k ohm impedance or resistance of the meter in parallel with the 50 k ohms of R2. So what happens now? Remember our voltage divider formula? It was V is equal to V applied times R over RT, right? Well, here it's REQ. V applied is still 50 volts times our REQ of 2 k ohms. No, 25 k ohms. 25 k ohms. 25 k ohms over our total of 50 plus 25, 75 k ohms. Which when you do all the math on this, that takes you to basically one. Right, just 25. I calculated this wrong. Let me quickly. That's going to be about 47 volts, I think. 25 divided by 50. No, 25 divided by 75 times 50. Yeah, it's 16.6. Yeah, that's right. I did have it right. 16, approximately equals 16.7 volts. So we were at 25 volts unloaded, and we put the 1 milliamp movement. We went to 16.7 volts. So a significant drop there, wasn't it? Now we're going to try a couple other different resistances for a meter. We're going to change this meter to a little more sensitive meter. It takes a little bit less voltage, or a little bit less current, excuse me. Leave R2 the same. We'll unhook that. We'll leave the voltage the same. We'll change our meter now. It's going to be what am I using here? Okay. So we're going to go to 50 microamp meter. 50 microamp. And we got the 2000 ohms, but we don't really care about that. But this is a so we take the 1 volt divided by 50 microamps, and we end up with 20,000 ohms per volt. So again, we want a 50 volt range. Well, 50. Yeah. 50 times 20,000 with much higher resistance here. We end up with, we actually have 1 megohm in here. So we need to find out, okay, now when we do the parallel resistance of the 50K and the 1 megohm, you can see the 1 megohm is not going to change it near so much. We end up with an REQ of 47.6 k ohms. We basically do 50 k ohms times, this is our parallel resistance formula for two parallel resistors, 50 k ohms times the 100 k ohms, 1000 k ohms, which is what a mega ohm is, and we divide that by 50k plus 1000k, which works out to be in, that's where we get our 47.6 k ohms. No, yeah, 47.6 k ohms. So that's where REQ becomes 47.6 k ohms. Now, it's pretty easy to see without doing any calculation. We didn't change that circuit near as much. We went from 50k to 47.6 versus we went from 50 to 16.7. And if we work out the formula, basically we say that got a new version of V2 here. V applied, still 50 volts. We'll put in here our new values here. We have a total now of 97.6k. And we have a equivalent here, which is taking the place of the original R2 of 47.6k ohms. And we calculate that out, we get 24.4 volts. And that is much closer to the 25 volts because we have a higher resistance meter, we're loading the circuit less, we're changing the voltage less because we're literally changing this resistance equivalent here by less. So the 25 volt open circuit with the 50 microamp movement, we end up reading 24.4 volts. And you can see that's a much more true to operating conditions reading than we had before. We're going to do one more. We're just given an impedance here of 10 megohm. We have a 10 megohm meter impedance. So now we have our REQ of this 50k, okay, 50k, and we'll put 10 meg here. These aren't in the same units to actually do the calculation. We'd have to put them into the same units, but I've already done the calculation, so I'm just going to put those values in here. And we end up the parallel of the 50k with the 10 meg, we end up with 24.9, which rounds to 25 k ohms. So you can see we're changing these values less and less and less. So we'll put the 24.9 k ohms here for our equivalent of R2 and our new 10 meg ohm resistance meter. And if we do the calculation here that we did before, well, this isn't right here. That's the numbers are wrong. Well, this was 49.8 k ohms. And that's what we got here for our REQ. Yeah, my 10 meg ohm in parallel, we get 49.8. Which is really pretty close to 50. It would, if you run it to one decimal place or or to not 1 decimal, to the units of ones, it would round to 50. Well, so we take this 49.8K equivalent in here, over our total 50. RT is now, when we add 50 plus 49.8, we end up 99.8. We add those up, or we divide those, multiply by 50, we end up with, there's where we get the 24.9 volts, which of course rounds to 25 volts if you run it to, which is pretty close to our original reading. But we'll, the 25 volt open circuit with the 10 megohm impedance meter gave us a 24.9 volt reading. And what do you see here? When we had the first meter, which was only had a 50K ohm impedance, we had 16.7 volts with the meter attached. When we put the more sensitive meter movement, we end up with a 1 megohm impedance. The 25 volts without the meter become 24.4 volts with the meter. Didn't change as much. Then we put the 10 megohm meter on there. It changed it only from 25 to 24.9. Now 10 megohms is actually pretty close to the resistance or the impedance of a lot of your digital multimeters that they make today. So that's why I put that example in there to show you. That's a fairly high impedance meter. It doesn't impact your readings that much, and most of the time that probably would not be enough for you to be able to tell the difference whether the circuit was working or not. It'd have to be a pretty precise circuit for that not to be close enough. And what are you taking voltage readings for? You're wanting to see if the circuit is working. If you think there should be 25 volts there and you see 3, something's wrong. Or you think there should be 25 volts there and you see 50, something's wrong. But if you think there should be 25 volts there and you see 24.8 or 24.9, you're probably going to think the circuit is probably okay. But we do have a formula. When you know the resistance that you're reading the voltage across, for coming up correcting this voltage. And basically the actual voltage is the voltage on the meter plus, okay, we're going to draw a voltage divider circuit here, R1, R2, and across that we have parallel. So this is very similar, some voltage source. So here we've got a voltage divider, and we have a resistance of our meter. I'll put a circle around that to help you see that that's the meter resistance. I'll put a box around it. I think a circle is a little confusing. A box for your meter, resistance to your meter, resistance 2, resistance 1. But the actual voltage would be the voltage you read on your meter plus R1, R2 over Rm times the sum of R1 plus R2. You see, that kind of looks like your parallel resistance formula, doesn't it? So let's do the example that we had. We had, I think this was with the, with the 1 megohm meter. 1 megohm meter, which was a 50 microamp movement. We had, we read 24.4. Right. Yeah, we had 24.4 volts we read. 24.4 volts. So if we put that meter in at 24.4 volts plus R1, R2, and our R1s were both 50K, weren't they? I'm just going to write 50K. I'm not going to put the omega there. 50K, you know it's resistance, you know it's ohms. So we do the 50K times 50K, these are ohms, and the 10, no, it was a 1 mega ohm meter, which is 10,000 K, or 1,000 K, plus 50K, times 50K plus 50K. And we work this all out, we end up, this comes out to be, there's some approximation here is why it doesn't come out perfect. We come up with 25.01 volts, which of course rounds very nicely to 25 volts, which we kind of know to be what the actual, okay, so let's put our 50 volts on here too. We know that the open circuit here is because they're equal resistances in our voltage divider, it's going to be half, so it's going to be 25 volts. We read 24.4 with our meter, and we did this formula of the voltage on the meter plus R1 times R2 divided by Rm times the sum of R1 plus R2, and we worked it all out. We got 25.01, which there was some rounding here, so that made this a little bit, but that still gets you very close to the 25 volts that you know it should be. So we've talked about voltmeters a bit, and we've talked about current meters a bit, and we see that voltmeters go across a component. You don't have to disconnect anything in the circuit, just put your leads on there and read the voltage. If these were my voltmeter leads, I could just, there we go, we got the voltage. And if it's a current meter, you got to break it open and put your meter inside the circuit. You'd basically take your meter and connect it up like that. So the current meter has to be in series, and because the current meter has to be in series, we want it to be really low resistance. We want to look at it. We want it to look to the circuit as much like that closed circuit that we originally had as possible. And being the voltmeter goes right across, we want it to be as high a resistance as possible so that we do not change the value of this R resistance that we're reading across any more than necessary. So the voltmeters, high resistance, and I'm putting parentheses here, impedance. They sort of mean the same. You'll find out more about that as time goes by. Current meters or amp meters. Current meters. Current meter we desire to be a low resistance, or we call that impedance. I'm putting a little arrow here going up for we want high resistance. Here, a little arrow going down, we want low resistance. So the voltmeter, we want to be high resistance or high impedance, so it does not change the resistance of the components you're measuring very much, so the voltage don't change much. For current meters, we want to be low resistance or low impedance because they're going to go in series. We don't want to change the total resistance of the circuit very much because we do not want to change the current. If we change the total resistance, we change the current. So the less we change the total resistance, in other words, why we want the lower resistance current meter, the less we change the actual current. And for the voltmeter, the high resistance, the less we change the actual resistance, the less we change the voltage reading. So that's why we like high impedance or high resistance voltmeters, low impedance or low resistance current meters. We've talked and we've done some examples. We designed a voltmeter multi-range one, done some examples. We looked at the range switch, how it selects different combinations of resistors to get a different total multiplier resistance. And we did three different impedance meters. We did one with a 1 milliamp movement, one with a 50 microamp meter movement, and we saw how that the meter that needed less current to operate impacted the voltage readings less. And when we did one with just an arbitrary 10 meg ohm impedance, which happens to be pretty close to the input impedance of a lot of your digital multimeters, so that's why I selected that value to talk about. And we've seen how as we got more and more resistance in our meter, we had less and less change on our actual voltage. We did a way of calculating what the voltage would be if we know the resistance here and the impedance of the meter, and we have a meter reading. Probably, your 10 meg ohm, this is 10 meg ohm digital multimeter, DMM, typical 10 meg ohm. That's a 50k ohm. Well, that's 10 meg ohms is 10 million ohms, right? Divide that by 50k ohms, which is 50,000 ohms. Let's throw off 4 zeros on each one, so 5 into 1,000, 5 goes into 1,000, that goes in there 200 times. So when we had 200 times the impedance of our meter as the resistor we were measuring across, we didn't have much change. And actually, with the 50 volt, what did I have there? 50, what was our impedance of our meter when we had the 50 microamp range? Yeah, that was 1 meg ohm. When we did the 50 microamp movement, then 50 microamp movement, we had a 1 meg ohm impedance, and that's still 20 times the 50k, and we didn't have too bad a change there either. When we had the 1 milliamp movement, we had 1,000 ohms, we had 50k ohms, and now they were a match, and that made a pretty significant change. That made it 2/3 or so of what it should be. 16.7 divided by 25. Yeah, that made it about 2/3. When we had the 1 milliamp movement, our voltage reading was only about 2/3 what it should have been. When we had the 50 microamp reading, we had 24.4. Then it was about 97.6%. And when we had the 10 meg ohm reading, we had, it was 24.9, right? 24.9 divided by, now it's up to 99.6%. So basically 67%, 97%, and 99%. So you can see as we increase the impedance of our voltmeter, we got better readings. With a low impedance 50k ohm total, we had 67% reading we should have. With the 50 microamp, the 1 milliamp movement, the 20,000 ohms per voltmeter, we had 97% of what our actual reading should be without the meter in there. We had the digital multimeter with the 10 meg ohm impedance, we had 99%. So you can see how high resistance, high impedance is a good value for a voltmeter. Anyway, I think that covers it for today. It was good talking to y'all. Thanks for coming back, and be sure to like and subscribe. And until the next time, keep on learning. Hello. At about 48 minutes and 55 seconds into this lecture, I realized I made a mistake on a formula that I put on the board. I had a voltage source, and we had a voltage divider circuit. R2, and we had a meter across this circuit. We're reading the voltage across R2, and so basically I had a voltage source V. We had a resistor 1 and resistor 2 formed a voltage divider. We're reading, this was the resistance of a voltmeter. We're reading the voltage across R2 with that voltmeter, and I was giving you a formula for making a correction for the amount of voltage change caused by the loading effect of the voltmeter. And what I put up on the board was voltage equals voltage on the meter, the amount what you read on the meter, plus R1 R2 divided by Rm times R1 plus R2. This would be the voltage you read on the meter. This is R1 and R2. This is R1 plus R2 again, and I'm pointing out this looks very much like your parallel resistance formula. This was the resistance of the meter. If you use this formula and calculated out the example I did, you would find that it wouldn't come out correct, and the reason was I left off Vm, the voltage on the meter. So the correction factor would not be correct. I'm going to underline this. This was the piece I failed to put in there. And I'm going to give you one more thing about this formula. You could factor this out too. You could rewrite this formula. You could say that the voltage, the actual voltage would be voltage on the meter times 1 plus R1 R2 over Rm times R1 plus R2. So basically what I've done here, and you really wouldn't have to do this, but being I'm messing around with it, I like to point it out. I factored the Vm out of here, which left just that. I factored the Vm out of here, which just left 1. If we were to distribute the Vm, we'd multiply 1 times Vm, we'd get Vm, and we distribute the Vm to this thing, we would get R1 R2 over Rm times R1 plus R2 times Vm. So we get right back to here by distributing the Vm. But that's the most important thing. I'm going to circle this. I left this out. When I did my calculations on my notes prior to doing the lecture, I used it so my result was correct, but you wouldn't be able to get the same result without having that Vm in there. And so if we take this stuff off, where I did the factoring and the distribution, the important thing is this correction term has to be multiplied by what you read on the meter to make the thing work out. And like I said, I did all my calculations on my notes correctly, but when I wrote the formula on the board, I neglected to put that term right there, and I don't want to lead you guys astray. Anyway, thanks again. Have a good day.